Hello students, in this video we'll find the Schwarz Christoffel transformation for the region that involves a large sink in a particular strip, and then use that to find the streamlines of a flow where there's a sort of a large channel which the ship can sink into. So let's consider the region. Geometrically, R. I'm just going to draw it. So what we're going to do is we're going to go all the way over here to a point, let's call that point negative A. And then what we're going to do is we're going to go all the way down like this. And we're going to come back up at positive A, like that. There's our region. So in other words, I imagine that I have a sort of a shipping lane over here, and there's like an off-ramp. Right, so imagine there's a river over here, and that's the channel that goes like the marina, basically, right? Excellent. So there's your region R. Of course, this region's a degenerate region, right? So R is a degenerate polygon. Very degenerate. And what I'm going to do to figure out the Schwarz Christoffel for this, I have too many infinities basically, right? So I need to basically artificially construct this region as a limit of other regions. So what I'm going to do is the following. I'm going to imagine that there's a point over here, W. Let's call that point over there IB, right? And what I'm going to do is I'm actually going to consider this region over here with these three vertices, with negative A, with IB, and with positive A, and that's where, let's assume that that's negative IB, right? Because I want it to be negative, okay? So what's going to happen is as I let B go to infinity, as B goes to infinity, we get the region R. So as B goes to infinity, we get the region we want. Okay? And so what I'm going to do is now, we're going to do the following. So we're going to take Z equals -1. Z equals -1 is going to be my point that goes to A. My Z equals 0 is going to be my point that goes to IB. And my Z equals 1 is going to be my point in Schwarz Christoffel that goes all the way over here to A. So those are going to be my vertices, right? So my vertices over here in this region R are going to be negative A, negative IB, and positive A. So we should note here, of course, that A is greater than 0 real, and B greater than 0 real. Both real. Okay, excellent. And so now we can write down our Schwarz Christoffel mapping. We need to find the exterior angles though, right? So I have three exterior angles to consider, right? I have this exterior angle over here, alpha. I have this exterior angle over there, beta. And then I have this exterior angle over here, gamma, okay? So what are our exterior relationship rules, okay? So I have alpha plus what? The interior angle over here is almost something that's very, very close to what? I'm going to write 3 pi over 2 in the limit is equal to pi. And this equation is true as beta goes to 0, beta goes to infinity, right? That equation is true as beta goes to infinity. Okay, because as beta goes to infinity, this line over here is getting more and more flat, right? And so what this tells us that alpha is going to be equal to what? It's going to be equal to negative pi over 2. That's going to be, of course, a positive exponent in Schwarz Christoffel, right? What about beta? Beta plus what? Beta plus, wow, that's very, 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 very small. Very, 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 very small. So what do I have over here? So the exterior angle, that's the exterior angle over there. And then plus a really small interior angle, something that's basically close to 0, is equal to pi, right? And this, of course, is true as beta goes to infinity, as B goes to infinity. And so this implies that beta is equal to pi. Okay, excellent. Of course, I should, if I'm being very, very careful, I have to put like an epsilon here, an epsilon here, an epsilon here, and then so let epsilon go to 0. So that epsilon goes to 0 as beta goes to infinity, and then I can write that these things more formally, right? Okay. And then finally, by the same reasoning, gamma plus what? It's gamma plus 3 pi over 2 equals pi, as true as beta goes to, as B goes to infinity. And that implies that gamma is equal to negative pi over 2. Okay, excellent. Now I can write down our Schwarz Christoffel. So what's our Schwarz Christoffel for this? We're going to have f prime of z is equal to what? Is equal to a. And then we're going to have a z plus 1 to the power what? To the power 1/2, we're going to have a z to the power -1. We're going to have a z minus 1 to the power 1/2. And there we have it. That's our Schwarz Christoffel mapping over there. Beautiful. Now we need f to find the streamlines. Okay? And so, of course, as we've seen before, what we can do to find f is we can integrate it as we would in Calc 2, right? And then that formula has to be the same as the formula for f in the entire region by analytic continuation, right? That's a very powerful result, right? If I can prove it on a subset for a subintegral, right? I have a formula on an interval. The formula has to remain valid in the entire complex plane, right? Because two formulas have to agree by the identity principle, and so I can analytically extend that formula, okay? Excellent. And so what's f going to be? So f of z, informally first, is going to be a, the integral. What are we going to have? We're going to have a z squared minus 1 square root of z squared minus 1 over z dz. It's been a long time since I taught Calc 2, but this looks like a trig integral, right? So I'm going to let z be secant, right? So let z be secant, square root of secant squared of theta minus 1 over secant of theta. If this was a Calc 2 class, I'd have to draw a triangle, right? It's not Calculus 2 class, it's a complex variables class, right? So we can just do this integral fast, right? I'm not good where I can do this in my head. I'm good enough to just do the thingamabob, do the ordinary integral. Okay, and then the derivative of secant is what? Is secant theta tangent theta. Okay? Secant cancels out, that's tangent, right? So this is a integral of tangent square root of theta d theta. And now tangent, of course, is just secant squared minus 1. Right? Integral of secant squared is tangent minus theta. Great. All right, so it is this, and of course plus b. Plus b. So therefore, this is equal to what? This is equal to a. The tangent, of course, the tangent is going to be the square root of that thing, right? The square root of z squared minus 1. That's tangent. And then minus theta, right? And what's theta? Well, theta is the inverse secant, so it's going to be the sine inverse of 1 over z, right? So theta is going to be the sine inverse of 1 over z. It's better to put it in terms of sine inverse secant, right? Plus b. Okay? All right, so what's going to happen over here? So I'm going to plug in the points -1, and we'll plug in -1 to get negative a. So negative a is f of -1. And that's going to be what? That's going to be a. When I plug in -1, I get negative the sine of what? The sine inverse of -1 is negative pi over 2, right? So that turns into a pi over 2 positive, plus b. And then positive a is f of 1. That's going to be a. And then the sine inverse of 1 is pi over 2 plus b. Good. If I add this equation over here to this equation over here, where's my negative? Oh, but there's also a negative, right? So that's a negative, right? Because there's a negative over there. Perfect, that's negative. So if I add these two equations together, what's going to happen? The a and the negative a are going to cancel out. The a capital is going to cancel out. So that's going to force b to be 0. So b is going to be 0. Okay, so if b is equal to 0, what does that tell me about a? So b is equal to 0. And that tells me that a is negative what? Negative 2a over pi, like that. Okay, good. Now we have our mapping, right? So now I can fill that back in over there, fill that value of a, and that value of b is gone now, right? And then you have your conformal mapping onto that region, okay? Excellent. All right. And so now what? And so now what this allows me to do is we can sort of see, now I have a formula for the streamline. So if we were to simulate this, if we replace z with t plus ic, for c is a constant, for t between negative infinity and infinity, we're going to get exactly the streamline. So here's our region. Our region looks like this. And what's our flow going to do? Our flow is going to go something like this. Our streamlines are going to do like this. And of course, those are the streamlines. If I let the real part be constant, and vary the imaginary part, I get the equipotential surfaces, right? I don't know what they exactly look like, but that sort of look like, in some sense, like that. Those are the equipotentials. And these things over here are the streamlines. And that sort of makes intuitive sense, right? If there's an incompressible flow, the flow tends to want to follow the predominant path of the upper half space, right? Of this upper region over here. So what's going to happen is as you go through the channel, there's going to be an attractive way. There's no source, so there's no source or sink over here. So I can't draw anything, I can't draw it deep into the channel. I can go fairly deep if I get really, really close to the axis, right? Where I'm going to be attracted to the boundary, because the boundary has to stick to itself, right? So in other words, the streamline close to the boundary is going to get as deep as to get deeper and deeper and deeper, you have to be very, very, very close to the boundary, right? There's an attractive force of the boundary, right? There's no slip condition on the boundary, but the point is that no matter how close to the boundary I am, I'm always going to get out of that well and go back into the main part of the channel. So this is a perfect example of basically using some very, very simple calculus and a degenerate region for Schwarz Christoffel to get very, very useful information about like a fluid flow in a region that's actually sort of a relevant region to consider a fluid flow in. Thank you very much.